Hello everyone. Hope you are doing very well. So as you all know that today we are going to cover the theory part 7 of chemical kinetics chapter. So let's start our today's topic, that is NCERT chapter 3 chemical kinetics theory part 7, which is and today we are going to cover the NCERT section 3.5 along with the NCERT exercise 3.9, 3.14, 3.19, 3.23 and 3.29. So let's begin. So this is the disclaimer. What's the objective of today's? So objective, after attending this lecture, you will be able to describe the collision theory. So we will study in detail what is collision theory in today's lecture. The topics which we are going to cover today according to the NCERT are: the first one is the section 3.5 collision theory of chemical reactions. In this we will talk about the collision frequency represented by capital Z, then orientation factor, then illustration of steric factor. Then we will see some in-text question from 3.7 to 3.9. And then we will also practice some exercises questions from 3.9 to 3.29, included 3.14, 3.19, 3.23. And lastly, we will see the summary and key points to remember according to the today's lecture, whatever the content we are going to study. So let's begin. Our first topic, 3.5 collision theory of chemical reactions. So Arrhenius equation is applicable under a wide range of circumstances. So as you know that we have covered about the Arrhenius equation in our previous theory part. So here we are studying the collision theory, in which we are saying that Arrhenius equation is applicable under a wide range of circumstances in our chemistry. So it does not account for proper estimation of number of collisions. If you want to estimate the number of collisions, okay, that in a chemical reaction, what are the number of collisions which are happening to forming the particular or a suitable product. So Arrhenius equation does not account for the proper estimation of number of number of collisions, have no accountability for orientation or steric factor. Also, it does not account, or it does not have any accountability for any orientation in a chemical reaction or steric factor. Max Strodz and William Lewis in 1916 to 1918 provides a greater insight into the energetic and mechanistic aspects of reaction. So these are the two persons, Max Strodz and William Lewis. They in 1916 to 1918 provide a greater insight into energetic and mechanistic aspects of the reactions, that how you can visualize the reaction in form of their energetic and the mechanistic. So they developed the collision theory, which was based on the kinetic theory of gases. So in a very starting of our chemistry, we have studied the kinetic theory of gases. Now the collision theory which we are going to study is based on this kinetic theory of gases. So according to this theory, the reactant molecules are assumed to be hard spheres, and reaction is postulated to occur when molecules collide with each other. So according to the collision theory, the reactant molecule which are participating in our chemical reaction are assumed to be hard spheres. We assume them to be hard spheres. Spheres means circular thing, okay, having a volume or density. So hard sphere, and reaction is postulated to occur when the molecules collide with each other, and those reactant molecules will going to collide with each other, and when the molecules collide with each other, the reaction is postulated and the products formation will happen. Now let's talk about the collision frequency. It is represented by the symbol capital Z. So the number of collisions per second per unit volume of reaction mixture is known as collision frequency. So as I said that the collision frequency is basically representing the number of collisions per unit volume of reaction mixture. That means during a reaction when reaction is undergoing, how much number of collisions or perfect collisions are happening for the making of the product. Okay, so number of collisions which are happening per second per unit volume of reaction mixture is known as collision frequency. Okay, so frequency is even determine or describe in terms of time. So collision frequency is basically the collisions which are happening per second per unit volume in the reaction mixture, and that is also denoted by the capital Z. So according to the Arrhenius equation we have studied, the energy should be enough during the collision for the reaction to takes place, right? So according to the Arrhenius equation, the energy that should be enough, that means complete or enough energy should be there during the collision for the reaction to takes place. For reaction to takes place means for the production of the products. Okay, this is as per the Arrhenius equation. So collision frequency was introduced in this equation to account for the number of collisions. Now collision frequency introduced in this equation in the collision frequency to account for the number of collisions, that how much number of collisions is happening during a chemical reaction between the reactant molecule which we are considering as a solid spheres to form the products. Okay, now for a biomolecular elementary reactions, that means when the reaction is happening and we have the reactant more than 2 or 2 or more than 2. So for a biomolecular elementary reaction where the two reactants are combining together, here we are representing them as A and B, and they are combining and forming products. So rate of reaction for this is can be expressed as rate is equals to ZAB e to the power minus EA by RT. Okay, so rate of reaction for this biomolecular elementary reaction can be represented as rate is equals to ZAB e to the power minus EA by RT for this particular reaction. And this is a NCRT equation marked as 3.23. Now here ZAB basically representing the collision frequency of reactants A and B which are present in this reaction, and e to the power minus EA by RT represents the fraction of molecules with energies equal to or greater than EA. So this is the equation for the rate of reaction for this biomolecular elementary reaction, and in this rate equation or rate of reaction equation, ZAB is representing the collision frequency of the reactants. That means per second per unit volume, what is the frequency of the collision between the reactant molecules A and B, and this term, the other term which is e to the power minus EA by RT, this term is representing the fraction of molecules with energies equal to or greater than EA. EA is activation energy. Okay, so this rest of the term e to the power minus EA by RT is representing that how much fraction of molecules in our reaction with the energies equal to or greater than EA are there, activation energy. Okay, now comparing with the Arrhenius equation, we can say that A is related to collision frequency, right? Because we just have seen that rate of the reaction is given as ZAB, which is representing the collision frequency, times e to the power minus EA by RT, right? We just have seen that equation. Now, if you remember the Arrhenius equation given by K is equals to A e to the power minus EA by RT. So both equations are same. So if you compare that equation with Arrhenius equation, we can say that the A which is present in the Arrhenius equation is related to the collision frequency, which is representing by ZAB in our previous equation, right? So K is equals to AE minus EA by RT. This is the Arrhenius equation, and this is also the NCRT equation marked as 3.18. EA is representing the activation energy. A is representing the Arrhenius constant in this Arrhenius equation. The rate is equals to ZAB e to the power minus EA by RT, which is the NCRT equation 3.23. Now this equation we just have seen, and if you relate or compare this rate of reaction equation with this Arrhenius equation, you can see that A present in the Arrhenius equation is related to the collision frequency, because another terms are same in both the equation. So K times R is equals to ZAB e to the power minus EA by RT, right? So rate is equals to ZAB e to the power minus EA by RT. Rate can be written as K times reactant concentration, right? According to the rate expression, rate can be determined, or rate can be written as rate constant multiplied by the concentration of the reactant, right, is equals to ZAB e to the power minus EA by RT. Rest are same. Now from here you can write it as K, that is rate constant, is equals to ZAB upon this reactant concentration in the divide and in the denominator multiplied by e to the power minus EA by RT. Okay, so why we are comparing these two equations? Because they are looking alike. Okay, and because before the collision theory we just have studied the Arrhenius theory and Arrhenius equation. So, and we are seeing that in both these theories or in both these equations, the equation are comparatively same. Okay, kind of same, because e to the power minus EA by RT, which is representing the number of fraction of the molecules, that is same in both the equation, right? And here rate is given as ZAB times e to the power minus EA by RT. In the Arrhenius equation, we have given the rate constant is equals to A times e to the power minus EA by RT. Now A here is replaced just by ZAB, and also the rate is given by KR, K multiplied by the concentration of the reactant. So K is also same here, only the remaining thing is the reactant concentration which present in the rate. Okay, so they both equation are kind of look alike, that's why we are comparing here. And we want to determine, if you want to determine the K value, that is the rate constant value, by using this rate of the reaction given by the collision theory, then you can determine that as K, that is the rate constant, is equals to the collision frequency of the reactants ZAB divided by the reactant concentration multiplied by e to the power minus EA by RT, right? Okay, now let's talk about the orientation factor. So all the collisions do not lead to the formation of products. Okay, so when a reaction is happening, the reactants are undergoing different collisions in different orientations. Okay, what does this word orientation means? That what is the placement of the reactant molecules with each other to collide in a particular direction so that they will form the product. That's why here it is written that all the collisions which are happening in a reaction do not lead to the formation of products. That means it is not necessary that every collision will lead to the formation of the product. Okay, so a particular orientation is required in a particular direction for the collision to happen between the reactant molecules to get the product. So the collisions in which molecules collide with sufficient kinetic energy, okay, they should have sufficient kinetic energy in the molecules which are colliding, which is called as threshold energy. That minimum kinetic energy or sufficient kinetic energy is called as threshold energy, by which the molecules are colliding with each other. Okay, and proper orientation is also important, so as to facilitate the breaking of bonds between the reacting species and the formation of new bonds to form the products are called as effective collisions. So what we are saying, that the molecules which are colliding with each other, they should have sufficient kinetic energy in them, which is known as threshold energy. It has the name threshold energy. And they should have proper orientation so as to facilitate the breaking of bonds between the reacting species, so that the two reactant molecules which are reacting together, that means the reacting species, the bond which is breaking or binding those two together to form a product, and formation of new bonds to form products. Okay, so if bond is breaking or even forming between the reacting species, that is going to be facilitated by these two factors, that the colliding molecule should have the sufficient kinetic energy and the proper orientation. Okay, and are called as effective collision. Those type of collision in which all these conditions are satisfied, they are known as effective collisions. To account for the effective collisions, another factor known as P, which is called as probability or steric factor, is introduced. Okay, so to account for effective collision, that means if you want a effective collision in a chemical reaction, another factor which is also considered as P. P is representing the probability or the steric factor. Okay, so P is known as the steric factor or the probability. That means what is the probability of formation of the product after the molecules is having the sufficient kinetic energy and the proper orientation. Okay, so that is the P factor, that is the probability or steric factor. It takes into account the fact that in a collision, molecules must be properly oriented. So we have to consider this case, that in a collision, when the collision is happening between the reacting species, the molecule must be properly oriented. Okay, so the molecule should be properly oriented. That means orientation should be correct. They should have the minimum amount of kinetic energy to react. Okay, so this is a particular condition, you can say, that you have to be considered in a collision. So rate, which equation which is given as PZAB e to the power minus EA by RT. So we also add a factor P here in this equation. In collision theory, activation energy and proper orientation of molecules together determine the criteria for an effective collision and hence the rate of a chemical reaction. So in a collision theory, activation energy and proper orientation of molecules both determine the criteria of effective collision. That means whether the collision is effective or not, that means whether the collision is perfect or not to form the product. Okay, so in the collision theory, the activation energy, that is E subscript A, and the proper orientation of the reacting species of the molecules together determine the criteria for the effective collision and hence the rate of chemical reaction. Okay, so rate will also be going to depend on this factor, which is effective collision, because if the collision will be effective, if the orientation is proper between the reacting species, they have proper activation energy in them, that means the rate of the chemical reaction will also be better, will also be faster, right? Now let's illustrate the steric factor. So illustration of steric factor: the formation of methanol from the bromoethane depends upon the orientation of reactant molecules as shown in the figure 3.12. We will see. So The proper orientation of reactant molecules lead to bond formation, whereas the improper orientation makes them simply bounce back and no products are formed. So, if you are making methanol from the bromoethane, okay, methanol means CH3OH. If you are forming the methanol from bromoethane, that is CH3CH2Br, depends upon the orientation of reactant molecules. So, this formation of methanol from the ethane, bromoethane, is going to depend upon the orientation of reactant molecules, that the reactant molecule is whether properly oriented or not to get the correct product. The proper orientation of reactant molecules will lead to bond formation, whereas improper orientation, in case if you oriented improperly the reactant molecules, that will makes them simply bounce back. That means the improper orientation will not get any product. Okay, they will bounce back and no products are formed. So this is the figure 3.12, which is a diagram showing the molecules having proper and improper orientation. So if we have a molecule of bromoethane, that is, okay, bromomethane, that is CH3Br, and you are reacting it with the hydroxyl ion, it is converting to CH3OH methanol and also releasing one bromine ion, right? Now, if you are taking this bromomethane and hydroxyl ion and you are doing improper and proper orientation between the reactant molecules, what are the cases and what are the products that you are getting in both the cases? So in the proper orientation, the intermediate is forming like this. How? So basically, you know that in the bromomethane molecule, the bromine is electronegative, right? So it will going to have a partial negative charge on it. Other than that, comparatively the carbon is less electronegative to the bromine, so it will having a partial positive charge. Okay, this partial charges between the carbon and the on the carbon and the bromine makes their bond weak, due to which it is effectively breakdown, right? So the breakdown tendency of the carbon bromine bond will increase after this charge distribution. And we have also a anion here, that is a nucleophile OH negative. So if you do a proper orientation, then what will happen, this intermediate will form. Intermediate is shown by closing them in this big brackets, square brackets. So CH3, Br and OH. What will happen, this bond will dissociate, this bond will break, C and Br, due to this partial charges formation on the carbon and the bromine. And this hydroxyl ion, because it is having a negative charge, it's a nucleophile, it will attack on the carbocation, because when this bromine will remove from the carbon, a positive charge will come on the carbon, right? And this nucleophile will attack on that carbocation, this positive charge, and this intermediate will form. The intermediate is showing the line bonds and the dotted line bonds, like so. Dotted line bonds is representing that the bond is either breaking or forming. Okay, so if you can see, we have a partial positive charge on carbon, partial negative on bromine, and partial negative on the hydroxyl ion. Other than that, H bond are stable. The dotted bonds are representing that carbon bromine bond is breaking and carbon hydroxyl bond or carbon oxygen bond is forming. So this is showing the intermediate position. And then after the breaking or the formation of the bonds in this particular intermediate, you will get the product as methanol, right? CH3OH, and the bromine ion will release. Meanwhile, if you do the improper orientation, what will happen? So basically, this is the case that this is the reactant molecules having the partial positive and partial negative charge on the carbon and bromine, and we have the hydroxyl ion present, right? Now, if you improperly orient them, what will happen? They will bounce back, which are shown by these arrows. So they will bounce back and no products will be obtained. Okay, so orientation doesn't change the physical states. Physically they will be same, but their way of reaction between them, or their way of reacting between each other or with each other, will be different. They will differ. Okay, so like if you are considering the proper orientation, they are properly oriented, the bond is properly forming or breaking in their particular orientation or direction, right? But if you are placing or or orienting the reactant molecules improperly, then they will not react with each other. They will bounce back from each other, and no product is going to obtain because they are not reacting with each other. Okay, the physical state will remain same. If this is a nucleophile, it will remain nucleophile. If this is a bromo, you can say bromoalkane, this will remain bromoalkane. Okay, so this is the diagram which is showing the proper and the improper orientation effects and the products. That what is the cases that if you are following the proper and the improper orientation in a reaction or between two reactant molecules. Okay, so let's see an in-text question which is marked as 3.7 as per our NCERT textbook. The question is saying that what will be the effect of temperature on the rate constant? Okay, so rate constant is represented by small k and the temperature. So what is the effect of temperature on the rate constant? That means if you increase or decrease the temperature, how it is going to affect the rate constant in a reaction. That is, you have to tell. So you have given some time, try to analyze this, and then we will see the correct answer. Okay, let's see. So for this given question, if you want to write the effect of temperature on the rate constant, it is nearly doubled with the rise of 10-degree rise in temperature. This we have covered, right? That if you are raising the temperature in a chemical reaction, if you are providing more, or you can say, let's say 10 degree, if you are increasing the temperature by 10 degrees Celsius in a chemical reaction, the rate of the reaction or the rate constant of the reaction is going to be doubled. That means K will become 2K. Exact dependence of rate of chemical reaction on the temperature is given by Arrhenius equation. Now, if you want to find out the exact dependence, that how the rate of chemical reaction is going on, is going to affect on the through the temperature, that is given by the Arrhenius equation, which is given as K is equals to A e to the power minus EA by RT. Right, K is a rate constant, A is Arrhenius constant, E to the power minus EA by RT, where EA is the activation energy, R is a gas constant, and T is the temperature. So this equation is representing the NCERT equation 3.18. So where the A is a Arrhenius factor or the frequency factor, you also call the A as Arrhenius factor. The T is representing the temperature, the R is representing the gas constant, the EA is representing the activation energy. So generally we if you want to know the exact dependence, that how the temperature is going to affect the chemical reaction, that you will determine by using this Arrhenius equation, because it is having rate constant and temperature in it, right? So K is going to affect through temperature, and you can determine this by using the Arrhenius equation, which is given by this. So let's see our next in-text question, which is marked as question 3.8. The question is asking that rate of chemical reaction doubles for an increase of 10 Kelvin in absolute temperature from 298 Kelvin. So the chemical reaction rate doubles for increase of 10 Kelvin in the absolute temperature from 298 Kelvin. Okay, so from the 298 Kelvin temperature, which is absolute temperature, if you increase the 10 Kelvin temperature, okay, the rate of a chemical reaction is going to be doubled. Now calculate the EA, that is, calculate the activation energy. So here also you can use the Arrhenius equation, right? Because there the activation energy is given. So you have given some time, try to solve this, and then we will see the correct answer, how you can solve this, the correct way to solve this. Okay, let's see. So for this question, it is given that T1, the absolute temperature, is 298 Kelvin, right? It is already given in our question. You are increasing it by 10K, right? So T2 will be 298 plus 10 Kelvin, right? So 298 plus 10 is 308 Kelvin. So T2, that is temperature 2, will become 308 Kelvin. Now, rate of reaction will double when the temperature is increased by 10 degree. So the rate of reaction is going to be doubles when the temperature is increased by 10 degree, right? It is also given in our question. It is also mentioned. Therefore, the K1 is equals to K. Okay, so K1 is equals to K and K2 is equals to 2K. K1 is the rate constant which we are considering during the T1, during the absolute temperature, which is equals to K. Now K2, the rate constant 2, is we are considering at the T2 temperature, which is 2K. Okay, so K1 is K, K2 is 2K, and the reaction is, or the rate of the reaction is doubling when the temperature increased by 10 degrees Celsius. So at K1, the T1 is 298, and at K2, the temperature increased by 10 becomes 308, and the rate constant will also doubles. R value, you know, which is a gas constant, 8.314 joule per Kelvin per mole, right? This is the rate constant value. This is a gas constant value. Now, if you know the Arrhenius equation, you can substitute these values in the equation. So a log of K2 by K1 is equals to EA upon 2.303 R 1 by T1 minus 1 by T2. Now this is the NCERT equation marked as 3.22. Okay, so if you want to find out the or if you have given the two different temperatures, and if you want to find out the rate constant, or inversely, if you are considering the rate constant value and you have to find out the two temperature, any one temperature, then you use this equation, which is log of K2 by K1 is equals to EA by 2.303 R times 1 by T1 minus 1 by T2, right? Now you know the K1 and K2 ratio, that K1 is K and K2 is 2K. You put it here. T1 you know, T2 you know. So on putting the values in the equation 3.22, we just have seen, we get log of K2 by K1 is this, which is equation 3.22, right? Now when you put the given values in this, you will get log of 2K by K is equals to EA upon 2.303 R multiplied by 1 upon T1. T1 is 298 minus 1 upon T2. T2 is 308, because after 10 degrees increase, the temperature will become 298 to 308. Right? Now only variable thing, or only the not only a variable thing or a non-determining thing is here is EA, which we have to find out. Already mentioned in the question that calculate EA. So EA you have to find out. Other than that, everything is numerical or the constant. So log of 2K by K will be EA upon 2.303 multiplied by 8.314, which is R value. Okay, 1 upon 298 minus 1 upon 308. After the LCM become 10 upon 298 times 308. Now you have to solve this. The K will cancel out from here. So this is the equation, right? K will cancel out from here, and you can multiply the 2.303 by 8.314 and 298 by 308. So log 2 will be EA upon this whole thing, same. So EA will be the denominator thing will go in the numerator in the product at the left hand side, and 10, which is present at the numerator with the EA in the product, will go in the denominator. So EA will be 2.303 times 8.314 times 298 times 308 times log 2 divided by 10. Now you have to solve this fraction. So it will be 52897, that is 52,897.78 joule per mole. So this is the value of the EA, that is the activation energy. Okay, and that is what we have to determine, calculate EA. So EA will be, because this is a very long value, so you can also compact it by writing it in another units, which is kilojoule, by dividing it by 1000. So 52.9 kilojoule per mole. Okay, so this is 52.9 kilojoule per mole. This is the value of EA. Okay, now let's see the another in-text question, which is marked as 3.9. The activation energy for the reaction 2HI giving us H2 plus I2, right, is 209.5 kilojoule per mole. So activation energy means EA for this reaction is given as 209.5 kilojoule per mole at 581 Kelvin. Now calculate the fraction of molecules of reactants which is having the energy equal to or greater than activation energy. So you have to calculate the fraction of molecules of reactants. That means from this reaction, what is the fraction of molecules of reactants which is having the energy either equal to or greater than activation energy, that you have to identify. You have given the activation energy already for this reaction, which is 209.5 kilojoule per mole, right? So how can you do it? You can first of all write the Arrhenius equation for this, and then from there you can determine the fraction of molecules of the reactants having the energy equal to or greater than activation energy. Okay, so you have some time, try to solve this, then we will see the correct answer. Okay, let's see. So for this given question, we have what is the given value. So first of all, we will see that what is the given value in this question. So we have given the activation energy for our reaction, right, which is 2Ki converting to H2 and I2. So the given value is the activation energy. So activation energy represents by EA is given as 209.5 kilojoule per mole, which is you can also written as 209,500 joule per mole. Now temperature is already given 581 Kelvin. So if you remember the Arrhenius equation, you have given the activation energy, the temperature, R is a constant, so so you can consider it already. So R is equals to 8.314 joule per Kelvin per mole, right? Now, the fraction of molecules of reactants having the energy equal to or greater than activation energy is given as. Now, we have to find the fraction of molecules of the reactants, right? That is given by X is equals to, so we are considering those fraction of molecule as X. So, X is equals to E to the power minus EA by RT. So in a Arrhenius equation, which is given by K is equals to A e to the power minus EA by RT, this term, that is e to the power minus EA by RT, is represents the fraction of molecules of reactants. Okay, so X will be that fraction which is given by e to the power minus EA by RT. EA you know, temperature you know, and R is also you know because it is a constant, gas constant. So when you take the log of both sides, the log of X will become equals to E minus EA by RT. Okay, log E will become 1. So log X is equals to minus EA by RT. Log X is equals to minus EA upon. Now here what we are doing, multiplying this term by 2.303. Okay, to convert the ln to log, because in the ln, this is basically logarithmic properties, that log is basically base 10, and here ln is basically log base e, right? In the ln, the base is e, so ln e is 1. So when you are having anything in the power of the log or the ln, it will go in the product, so this will come in the product. Ln base e will become 1. Okay, and if you want to convert the ln e or ln base e to the log base 10, you will have to multiply this by 2.303 rt. Rt is already there, right? So log X is equals to minus of EA upon 2.303 rt. Now this was the equation, right? So log X will be EA, you put the value 2.303 here, multiply by R value, which is 8.314, multiply by temperature. Temperature is 581 Kelvin, already given, right? Now when you solve this, it is coming out as minus of 18.8323. Okay, this is the value of log X which is coming out. So for the X value, that is only the fraction of the molecules which you want to find out of the reactants. So for X, you take the anti-log of minus 18.8323. Now you have to go to the tabular of the log or the anti-log to find the value of anti-log of this. Okay, or you can also say that log base 10 X is equals to this much, then X will be 10 to the power minus 18.8323. That is called as anti-log of this minus 18.8323. So X will be equals to, from here, 1.471 multiply by 10 to the power minus 19, right? So let's see our NCERT exercise question 3.9. The question is saying that a reaction is a first order reaction in A, that is a reactant. A is representing a reactant. So reaction is first order in A and second order in B. A and B are the reactants. First question, write the differential rate equation. You have to write the differential rate equation. Secondly, how is the rate is affecting on increasing the concentration of B 3 times. Second question is that you have to tell that how rate will going to affect if you increase the concentration of B reactant by 3 times. Third question is that how is rate affected when concentration of both A reactant and B reactant are doubled? When both are getting doubled, how the rate is going to affect? So you have given some time, try to solve this, then we will see the correct answer. Okay, let's see. So for this, exercise question. So the first question was that you have to write the differential rate equation. So according to the question, reaction is first order in A and second order in B. So the differential rate equation will be minus dr by dt is equals to k times the A concentration to the power 1 because it is first order, and B concentration to the power 2 because it is second order, right? Second question was that how rate is going to affect if you are increasing the concentration of B 3 times. So according to the question, the rate equation is this, that minus dr by dt is equals to k times A concentration and B concentration to the power 2 because it is second order according to the question. The part of the question is saying now that the B concentration is increased by 3 times, then how the rate is going to affect. So if you increase the concentration of B by 3 times, which is already given, then minus dr by dt will become equals to k multiplied by A concentration multiply by 3B because B concentration will increase by 3 times whole square, right? So this is how rate is going to affect if you increase the concentration of B by 3 times. And you can also write it as 3 whole square will, you can take common as 9. So 9 times Ka concentration multiply by B concentration whole square. Therefore, rate of reaction increased by 9 times because the initial rate is this, which is same here, but 9 in the product came. So rate of reaction will increase by 9 times on increasing the concentration of B reactant by 3 times. Now, in the third question, it was asked that how rate is going to affect when concentration of A and B both are doubled. So according to question, the differential rate equation will be minus dr by dt equals to k A concentration times B concentration whole square, right? This was the question. Now, if you increase or if you double the concentration of A and B both, then minus dr by dt is equals to k times 2A concentration. That means A concentration will be double, so 2A multiply by 2B whole square. You can write it as 8 times because 2 already you can take out, and 2 square will be 4. 4 times 2 will be 8. So 8 times K A concentration times B concentration whole square. That means the rate of the reaction is increasing 8 times. Okay, so we have determined the rate equation according to the given question. Then in the second question, if the concentration of B we have increased 3 times, the rate is increasing 9 times. And in the third equation, in the third question, if you are increasing the concentration of both A and B by double, by like you are doubling the concentration of both reactants, then our rate of reaction is increasing 8 times. This is how the rate is affecting when you are increasing the concentration of the reactants. Okay, so okay, according to the Arrhenius equation, first of all, the which is given by K is equals to A into e to the power minus EA by RT, right? K is rate constant, A is the pre-exponential factor, EA is activation energy, R is a gas constant, T is the absolute temperature. So how the temperature is depending, right? So basically the Arrhenius equation, taking the natural log, if you take the, because it is in the E form, right? K is equals to A into e to the power minus EA by RT. E is there, exponential factor. So you have to convert it into the log form, and when you take the natural logarithm of the Arrhenius equation, it will give you a relationship which is linear relationship between natural logarithm, that is log of the K, that is log K, and the absolute temperature, that is T. Okay, from there that will going to determine the activation energy and the T relationship. Okay, from there we have determined that yes, the temperature, with the increase of the temperature, the rate constant is affecting, which is increasing. Okay, so this is how we have determined the rate constant value by the temperature as per the Arrhenius equation. Okay, so because in the A, if you want to know more, because log can be easily, log value you can easily predict, E value will be there, then that is going to be, and also T is also in denominator, like E to the power minus A by RT, right, in the denominator. That will be difficult, so convert it into the log form. Then you know that if inside a log there is a positive thing, then its value is going to be small in the decimal, right? If there is a negative thing, that negative will come out outside, right? So that's how the log value is going to affect the overall value that is come out at the right hand side in the Arrhenius equation. And the T, which is present in the denominator, is going to affect the rate constant, right? So rate constant is basically for a reaction proportional to the exponential of uh, negative activation energy divided by the product of the ideal gas constant, that is R, and the temperature, that is T. And according to the Arrhenius equation, rate constant, reaction rate, increases with the increasing of the temperature. And we have also seen the graph also in the previous theory. If you remember, we have seen the graph where there was Arrhenius plot, and the plot was showing that the curve is increasing highest at some point, and for the T temperature it was that. And if you are increasing it by 10 degrees Celsius, then that the plot will broaden out at the right hand side and will cover the more fraction of molecules, remember? So from Arrhenius plot also you can determine the relationship between the rate and the temperature. Okay. So that's all for today's chemistry session. Thank you so much for joining this.